Welcome to the deep dive. Today we're plunging into this really fascinating intersection of truly cutting-edge technology and some, well, surprisingly human challenges.
Yeah, we've got two quite different stories lined up, haven't we?
We do. First, we're heading right to the edge of computing. There's a new breakthrough that, get this, promises to solve problems in minutes that would take today's best supercomputers longer than the universe has been around.
It sounds like science fiction, honestly.
It really does. And then we're going to switch gears completely. We'll look at a really common but kind of overlooked issue with tech many of us wear every single day. So our mission, as always, is to cut through the hype, get right to the core of what's going on with these innovations, these quirks, and figure out what they actually mean for you.
Exactly. We'll dig into Google's new quantum chip, Willow, look at those pretty audacious claims, but importantly, we'll also bring in some critical perspectives from other experts in the field.
Right, need that balance.
Definitely. And then, yeah, we'll shine a light on why your smartwatch might be acting up sometimes, and crucially, what you can actually do about it. Should be some real aha moments today.
Okay, let's do it. Let's break down this incredible claim about Google's Willow chip first. You hear numbers like 10 septillion years, phrases like faster than the universe is old. It just sounds, well, unreal. What's actually happening here?
Well, Willow is Google's newest quantum computing chip. It's a superconducting one, their most powerful yet, and it's specifically designed, they say, to build these large-scale quantum computers for problems we just can't solve otherwise.
Okay.
And that septillion years number, that comes from a very specific test, a benchmark computation they call random circuit sampling.
Okay, so it's a specific task.
Exactly. Willow did this task in under 5 minutes. The comparison is that Frontier, the fastest classical supercomputer we currently have based in Tennessee, would supposedly take, well, 10 septillion years. That's 10 with 24 zeros after it.
Wow, just hard to even grasp that scale.
At all.
Longer than the age of the universe, literally.
It really is. And, this isn't the first time Google's made claims like this. Back in 2019 with their earlier chip Sycamore, they had a similar thing, 200 seconds for the quantum computer versus, they claimed, 10,000 years for a supercomputer.
I remember that. But wasn't there some pushback?
There was, yeah. IBM particularly argued that actually a classical computer, if optimized correctly, could do that same calculation in maybe 2.5 days and with better fidelity, better accuracy. So this whole quantum supremacy debate, it's always had layers.
Right, it's nuanced. So what makes Willow different then? What are the actual advancements they've made this time around?
So Willow seems to tackle two massive problems that have plagued quantum computing. The first is errors. Quantum computers are just inherently more prone to errors than classical ones.
Why is that?
It's because their basic units, the qubits, exist in these incredibly delicate quantum states, very fragile. Think of it like trying to balance a needle on its point constantly. Any tiny disturbance can knock it off.
Okay, makes sense.
And historically, the problem was the more qubits you added to make the computer more powerful, the more error-prone it became. It was a scaling nightmare.
So more power meant more mistakes, essentially.
Exactly. But Willow apparently reverses that trend. Hartmut Neven, who leads Google Quantum AI, actually said, the more qubits we use in Willow, the more we reduce errors, which is huge.
Wait, how do more qubits reduce errors?
It's down to something called quantum error correction, or QEC. What they've managed to do is bundle multiple physical qubits together to create a single, more stable logical qubit.
Like having built-in redundancy or checking.
Sort of, yeah. These logical qubits are much better at detecting and correcting the errors that happen in the physical qubits they're made from. And they found that as they scaled the grid of these encoded qubits from 3 by 3 up to 7 by 7, the error rate was actually halved each time.
That is a breakthrough. Okay, what was the second big challenge Willow addressed?
That's related to coherence times. Basically, how long a qubit can hold its fragile quantum state before it just collapses back into a classical state, losing the information.
Right, how long it stays quantum.
Precisely. With Sycamore, that was about 20 microseconds. With Willow, they've pushed that to 100 microseconds, a 5-fold increase.
Still sounds incredibly short, but I guess in the quantum world.
It's a significant leap, yeah. And they say this improvement was partly enabled by their new dedicated quantum chip factory out in Santa Barbara. Better manufacturing, better control.
And the hardware itself, anything new there?
Yeah, they're using what they call tunable qubits and couplers. These are components you can adjust, which lets them perform operations, gates much faster, keeps error rates low, and even lets them sort of reconfigure the system on the fly if some qubits aren't behaving properly, these outlier qubits.
Fascinating. So it's not just speed, it's really about control, stability, scalability,
Yeah,
making the whole system more robust.
exactly. That seems to be the core message here.
So if they can actually reduce errors as they scale and keep things stable for longer, what does this mean looking ahead? What kind of real-world problems could this kind of technology, maybe not Willow tomorrow, but eventually help us solve?
Well, the implications are potentially enormous. One big area everyone talks about is encryption. Quantum computers, theoretically, could break the kind of encryption that protects, military secrets, financial data, everything.
The encryption we use today?
The encryption we rely on today, yes. Some researchers, particularly in China, have already published work suggesting how it could be done, so it could make our current methods obsolete down the line.
That's slightly terrifying.
It is a major concern, yeah. It's why there's a big push for post-quantum cryptography. But beyond that, the potential upsides are huge, too. Understanding the universe at a fundamental level, solving incredibly complex calculations in fields like pharmaceuticals, designing new drugs, or developing new materials for batteries, making them way more efficient, or even, potentially, helping us finally crack fusion power, problems that are just too complex for even the biggest supercomputers today.
So things that could really change society.
Absolutely. And you see that reflected in national security interests, too. Some quantum firms are specifically looking to build manufacturing here in North America, partly for that reason. Keep the technology close.
Okay, this sounds incredibly revolutionary.
Mm.
But as you mentioned, breakthroughs like this always draw scrutiny. Where does the expert skepticism come in? What are the caveats?
That's a really important question. So people like Professor Alan Woodward at the University of Surrey, they raise a flag about that specific septillion years benchmark.
The random circuit sampling one.
Yeah. He suggests that particular task is, well, almost tailor-made for a quantum computer. It's something they're naturally good at. So comparing it directly to how long a classical computer would take, you have to be careful not to compare apples and oranges, as he put it.
Meaning it doesn't necessarily prove quantum computers are faster for all kinds of problems.
Exactly. It doesn't automatically mean a universal speeding up compared to classical machines across the board. That's the caution.
Okay, so manage the expectations a bit there.
Right. But that being said, even with those caveats, pretty much everyone agrees that Willow is significant progress, especially as we discussed in quantum error correction. QEC has been this monster problem scientists have wrestled with for
The
decades.
scaling error issue.
Yes, and Willow seems to have genuinely managed to reverse that trend, making the system less error-prone as it got bigger by using those logical qubits. That's a really big deal.
So what are the actual specs they've achieved with Willow right now?
Okay, so the chip they reported on has 105 physical qubits, and they achieved an error rate of about 0.143% with their logical qubit implementation, which is, impressively low for this stage.
And it could hold its state for...
They demonstrated maintaining quantum data for up to an hour using error correction, which is crucial if you want to run longer, more complex quantum algorithms eventually.
Right, an hour sounds much more practical than microseconds.
Definitely a step in the right direction. So the long-term view from most experts seems to be, this is really encouraging. It shows QEC can work in practice, but we're still going to need much, much lower error rates and way more qubits, probably millions, for the truly game-changing quantum computers.
The ones that can tackle problems today's supercomputers genuinely can't touch.
Exactly. So we're still talking years, probably billions more dollars in research and development before these kinds of machines are, widespread or commercially routine. It's a marathon, definitely not a sprint.
What a journey, though, from these mind-bending speeds and quantum leaps to, well, sometimes technology bumps up against reality in much more everyday ways.
It's quite the contrast, isn't it?
It really is. Let's shift from the theoretical limits of computation to something super practical. A weird interaction many of you listening might have actually encountered without even knowing why.
Yeah, it's true. You have these incredibly sophisticated smartwatches, like the Apple Watch, packed with sensors. But they can sometimes be completely stopped in their tracks by something as simple as a tattoo on your wrist.
A tattoo? How does that work? especially for health tracking.
It comes down to the main sensor technology they use for things like heart rate. It's called photoplethysmography, or PPG.
Okay, PPG, what's that?
Basically, the watch shines a light, usually green or infrared, into your skin. Then it measures how much of that light bounces back or passes through.
Right, I've seen the lights on the back.
Exactly.
Yeah.
As your blood pulses through the vessels under your skin, the amount of light absorbed changes slightly. The watch detects these changes and calculates your heart rate.
Okay, simple enough. So where did the tattoo come in?
The problem is the ink. The pigments in tattoo ink, especially if it's dark ink like blacks and blues or even certain other colors like red, can actually absorb or scatter that light before it gets deep enough to reach your blood vessels.
Oh, so the ink essentially blocks the sensor's view of the blood flow.
Precisely. It acts like a barrier, preventing the sensor from getting a clear reading of those subtle changes in light absorption caused by your pulse.
So it's not just a minor glitch then.
Yeah.
It can actually stop the sensor working properly. What's the real-world impact for someone wearing the watch?
Well, the most common impact is inaccurate heart rate monitoring. It might show readings that are way off or just fail to get a reading at all, especially during exercise when things are moving around.
Got it.
It can also interfere with features like wrist detection, where the watch knows if it's actually on your wrist or not. If it can't detect your skin or pulse properly, it might think you've taken it off and lock itself, or stop sending notifications. Makes the watch seem really unresponsive.
Huh. I wonder how many people have experienced that and just thought their watch was faulty. Has Apple or other companies acknowledged this?
Yeah, Apple actually does mention it on their support website. They state pretty clearly that the ink, pattern, and saturation of some tattoos can block light from the sensor, making it difficult to get reliable readings.
Good to know they acknowledge it. So if you do have tattoos on your wrist, what can you actually do about it? Are there workarounds?
Well, the simplest preventative measure is if you're planning tattoos and wear a smartwatch, try to leave the skin on the top of at least one wrist clear where the watch sensor sits.
Okay, but if the ink's already there.
Then you can try a few things. Sometimes just loosening the watch band slightly can help. Maybe it changes the angle enough. Switching wrists if your other wrist isn't tattooed is obvious. Or even trying to wear the watch slightly higher up your arm, maybe on an area with less dense ink coverage.
Any other more creative solutions?
There is actually a pretty clever hack that popped up on Reddit. Some users reported success using these little clear epoxy bottle cap stickers. They're cheap, like maybe $10 online for a pack.
Epoxy stickers, how does that help?
The theory is you stick one directly over the sensor array on the back of the watch. It seems counterintuitive, but for some users, even with heavily tattooed wrists and newer watches like a Series 7, this apparently provided just enough of a consistent, clear medium for the light to pass through and get a reading. It somehow standardizes the surface the sensor sees.
Wow, a $10 sticker fixing a multi-$100 smartwatch issue? That's tech for you.
It really is. Sometimes the simplest physical solutions work for complex tech problems.
What an incredible deep dive today. Seriously, from Google's Willow chip, grappling with the fundamental nature of computation and, the age of the universe.
Right down to the ink pigments in your skin interfering with the light sensors on your wrist.
It really just highlights how all technology, doesn't matter if it's a quantum scale or something you wear every day, is constantly interacting with and sometimes limited by the basic physical properties of the world around us.
Absolutely. It's this constant push and pull between innovation and, well, physics. You can't escape the fundamentals.
Which leaves us with a really interesting thought for you, our listeners. As technology keeps advancing, just rocketing forward, what other seemingly small, maybe insignificant physical properties might suddenly pop up as unexpected barriers? Or, looking at it another way, maybe even create totally new pathways for innovation we haven't even thought of yet?
Something to definitely chew on.
Keep that thought with you. We'll be back with another deep dive soon.